Welcome to example number 10, Atwood's machine. In this question we have two masses, M1 and M2. We're told that M1 is the heavier mass, and what's going to happen is, since this is heavier than this one, then this M1 block is going to accelerate downwards and M2 is going to accelerate upwards. And we're asked to determine the acceleration of the masses. So let's go ahead and get started here. Now there are two ways of doing this problem. You can solve it as a system, and it's very fast if you do it that way. I'll do that at the end of the video, but the other way of doing it is to treat it individually. And when you treat it individually, then you can find other things such as the tension force. So I'm going to do it the long way first. So the first step we're going to do is draw a free body diagram. Alright, let's take a look at M1 here. What forces would be acting on that block M1? Well, you see a string is pulling it upwards, so you should realize that there's an upward tension force. And then there's a downward force of gravity. So I'm going to label that force upwards as F sub T for the tension force. Sometimes people label it as just simply capital T. And then over here, I'm going to label this as F sub G1. Don't just put FG, because really there are two weights in the problem. So you really do need to distinguish that they actually do have different weights. Okay, so now moving on to M2 now. And we're going to draw the forces over here. So we have an upward tension acting here. And then we have a downward force of gravity going down. So we'll label this one as F sub T. And then over here we'll label this as F sub G2. Alright. You'll notice that I was careful to draw the forces kind of at the appropriate length. So if you look at it, this body and this body here, the tensions here and here are both equal in size arrows. I tried to do that. Maybe they're not exactly the same, but they are roughly the same. And we're assuming that the pulley is frictionless and has no mass. And so that's okay to say that the tension on the right side of the string and the tension on the left side of the string are identical. Now the weights are not the same. You can see FG1 is bigger than FT, which makes it accelerate downwards. And FT here is bigger than FG2, which makes it accelerate upwards. I like to label the direction of the accelerations on my diagram, but I use a wiggly arrow because I don't want to confuse it with a force vector. So I'm going to draw a wiggly arrow downwards here for the acceleration of M1, downwards, and a wiggly arrow going upwards showing the acceleration upwards on M2. So it's also the direction of the net force on each of those bodies. Notice both of these bodies have the same accelerations as well as the same tensions. So after drawing the free body diagrams, our next step now is to apply Newton's second law to both bodies. Let's start with block M1. So I'm going to write over here block M1 so I know which one I'm using. So block M1, and we're going to apply Newton's second law. That's sum of the forces are not in equilibrium. They're giving you a net force that's equivalent to M1 times A. Now I think it'd be important to state what direction you are assuming to be positive, and you really have two possible choices. You can either choose going down as being positive, and that's what I've written over here because of a net force of MA, or I could choose up to be positive. It's up to you. If I choose up to be positive, then really I need to be thinking of this net force of being negative, or you could think of the acceleration being negative. So I'm really multiplying M1 times negative A. So therefore my net force is really negative M1A. So if I now sum the forces, then the force of tension, which would produce this net force of negative M1A down, that force of tension minus force of gravity is resulting in negative M1A. So sum all the forces along my y-axis, and I will get Ft minus Fg1, which is equal to negative M1A. So if I go a little bit further, I can write this as F sub T minus M1G. I'm replacing Fg with M times G, equals negative M1 times A. And that's about as far as I can get with this expression. If you look at it carefully, you might notice that we have really two unknowns. We have Ft that we don't know, and we don't know A. So really we need a second equation, and that's going to come from block M2 over here. So let's take a look at block M2 now. So block M2, and we're going to once again come up with a appropriate coordinate system. I'm going to use the same coordinate system that I have for M1. So I'm choosing a positive y coordinate system up, and so I'm going to be applying Newton's second law. Sum of the forces along my y-axis going to be resulting in a net force of MA. Be careful, you want to make sure that you indicate which mass it is, so it's M2 times A. And because the net force is upwards, that means the acceleration is upwards, right? Then we have a positive MA on the right side because we've chosen a y-coordinate system up. So now, summing the forces along our y-axis, we see that we have the force of tension up minus the force of gravity acting on block 2 down is equal to M2 times A. If we go a little bit further and express Fg2, we can have Ft minus M2 times G is equal to M2 multiplied by A. And once again, we have two unknowns. We have Ft and we have A. So there's our two equations and two unknowns. And since we're solving for the force of tension, or actually no, we're solving for the acceleration, we want to get rid of the force of tension. So let's write one of the equations so that Ft is by itself. Let's do that for block M1. So we're going to rewrite Ft all by itself. Ft would be equal to negative M1 times A plus M1 times G. I'm moving that over to the right side. And I'm now going to substitute this equation, we'll call that 1, into equation 2. So we're subbing 1 into 2 here. And so now what we'll do is replace Ft with negative M1 times A plus M1 times G minus M2 times G is equal to M2 times A. And now we can collect like terms. You'll see there's a term with an A here, and there's a term here with an A as well over there. So let's bring this term over to the right side. And so we'll end up with M1 times G minus M2 times G is equal to M2 times A plus M1 times A. And then if you collect like terms, you're going to have M1 plus M2 multiplied by A. And then we have M1G minus M2G. And then if we rewrite that, so A is all by itself, we have M1 times G minus M2 times G all over M1 plus M2, which is that expression over here. And you'll notice, if you look at it carefully, it's really the difference between M1 minus M2 times G. So it's the difference between the two weights of these two blocks, divided by the sum of the two masses, M1 and M2. And this kind of brings me to another way of solving this problem, by the way. So this is the way, what we just did is solving them individually, and we solved two equations and two unknowns. And that can be quite long, and sometimes you might find it much easier if you treat this as a system now. So to treat this as a system, we need to define a coordinate system that is around the entire system. So I've drawn a dashed rectangle to kind of illustrate that this is my entire system here. Imagine I have a coordinate system that starts here, goes all the way up, and then around, and then it continues to go down in this direction. So this axis, I'll call it the y-axis, is going up on the right-hand mass, and then it's coming actually down on the left-hand mass. So it's positive in the downward direction here for this M1 mass, but it's positive in the upward direction for M2G. I've chosen an axis that's in the direction of the acceleration of the entire system. I don't know if this helps, but maybe imagine that these two masses, this one's like flipped over here, and this one's flipped over there, something like this. And so this is my two bodies, and I've just drawn them out horizontally. Maybe we'll just put it over here. This is block M1, and this is M2, and let's show the forces acting on them. And M1, this force to the left here would be Fg1, because I've just drawn it out horizontally. This force Ft would be over here. This force of tension would be this one over here. And then the weight, Fg2, is over here. And we could also label the directions of the acceleration. M2 would be accelerating to the left, which is up in this situation over here. And M1 would also be accelerating to the left, which is down, actually, in that scenario here. And then you can see that if we wanted to show the system, I'll just draw a dashed rectangle around my entire system here. And now we just have to indicate our coordinate system like we did over here, which we'll put in the same direction as the acceleration of the system, going to the right. And so it would be positive in this direction. I can call that, well, just positive. Let's call it, that's our axis. You can call it an x or y axis. It really doesn't matter. So now we're going to apply Newton's second law to the entire system of M1 and M2. So you write sum of F, and I'm just going to indicate this is for the system, sum of the forces for the entire system, and would be equal to the mass of the system, which is really these two combined masses, M1 and M2. multiplied by A. So, or you could just simply write M times A, but then later on you'll need to replace M with M1 plus M2. And now, if you look at this, on the right side, we're still going to have M1 plus M2 times A, and then we're going to sum all the forces that are causing it to accelerate. Now, Fg1 would be considered positive because it's in the direction of our axis. So we have positive force of gravity. The weight of M1g is causing this acceleration. But Fg2 is going in the opposite direction, so that would be negative here, minus Fg2. Now, what about these tensions here? Well, one tension is to the right, which is positive, and this tension over here is to the left. And they're both inside my dotted rectangle, which means they're what we call internal forces. And these two internal forces are equal and opposite to one another. So they actually cancel one another out, and so we do not have the tension in our equation at all. So the equation is quite simple. Fg1 is really m1 times g. Fg2 is m2 times g, and that's equal to the mass of the system, m1 plus m2 times a. And then if you solve for a, you'll get basically this expression, m1 times g minus m2 times g, all over m1 plus m2. So that was a lot faster than treating them individually. But one quick note about this is that you will not be able to figure out the tension between these two bodies because they canceled out. So in order to find the tension, you will need to apply Newton's second law to one of the bodies, either this one or this one, and then you could find out the tension. Okay, and that's it for this example.